Okay, this is Lab 2, motion of a falling object. The important concepts will be Newton's second law and the drag force equation, along with the velocity update and position update formulas, which are derived from Newton's second law. The purpose and results. The purpose is to create two separate computational models, one with gravity and one with gravity and drag of falling motion, in order to compare them with an observed model. The results were that the model, which included drag alongside gravity, was more similar to the observed model. The significance of these results is that the model which included drag is more similar to real physical phenomena. In other words, in reality, gravity will not be the only force working on a falling object. Here's the video I used in Tracker software. The system was a paper ball. The initial conditions are on the right. The code, this one concerns gravity only. We are only accounting for movement in the y direction. The proportionality constant is 0, which represents air resistance. Yes, this is the second part of the code for gravity only. The important things here is the changes made in terms of the object's velocity. This has ended up just being the velocity update formula alongside the position update formula. So here's the code for gravity and drag. The main difference here is that the proportionality constant is different. The way that I got this number for B was basically just through trial and error, changing the value up and down for B until I got an ending position which was similar to the position that I got in my original observed model that I captured on Tracker. Another big change here is that the net force is changing, because originally we just had the force of gravity, now we have the force of drag as well, so we have to put this in there. So it's just the proportionality constant times the velocity of the ball. Then you add those two forces together and you end up getting net force. And if that was at terminal velocity, then it should be 0 at that point when it's at terminal velocity. So here is the data side by side in a chart made from Excel. The orange one right here is the observed model. The blue one is the gravity and drag, and the green one is gravity only. So we can see that the gravity and drag is somewhat more similar to the orange one than the green one. So what does this all mean? Terminal velocity is the maximum speed attainable by an object as it falls through a fluid. We can actually consider air a fluid. The computational model, which includes drag and gravity, models what terminal velocity would be. We can't say that we've reached terminal velocity within that observed model, but that said, if given enough time and given ample distance to fall, we would have reached terminal velocity. Such a model will predict terminal velocity because drag counteracts gravity in regards to falling objects. When terminal velocity is reached, the force of drag and the force of gravity are equal and opposite. So basically, your net force is 0. What if the object were thrown? If it had sufficient distance to fall, the object would eventually slow down to terminal velocity, considering that you threw it faster than terminal velocity, which is very likely. The terminal velocity will be the same as if it were dropped, though. The terminal velocity is not going to change. We don't have any kind of power over gravity or air resistance in the experiment that we're doing. So the terminal velocity of your system will still be the same, regardless if you throw it and it has to slow down, or you drop it and it has to speed up or slow down to get to its certain terminal velocity.